looking at is exponents, and we're going to start off today by looking at the exponential rules. Now the exponential rules, generally, hopefully you guys know them already, but I'm just going to do a quick review, and for some of you it might be new. The zero exponent rule basically says that any number taken to the zeroth power is equal to 1, right? No matter if it's a million, or negative a million, or 5. For example, 3 to the zeroth power is 1. Power rule. Power rule says that any exponent taken to another exponent, to combine the two exponents, we simply multiply them together. So for example, if I have 4 to the power 2 to the power 3, I just multiply these two powers together and I end up with 4 to the power 6. So remember, if we have an exponent to an exponent, we multiply them together. The negative exponent rule. The negative exponent rule basically says that if we have an exponent to a number to a negative exponent, we take the reciprocal of that number. So for example, 5 to the power negative 2 is 1 over 5 to the power 2. Right? We simply put it in the denominator. The product rule. Product rule says that when we have two bases multiplied together with different exponents, we simply add the exponents together. So for example, if I have x squared times x power 4, to combine them I just add 2 plus 4 equals 6, and I get x power 6. Quotient rule, similar idea, except instead of adding, we now subtract. So if I have a power m over a power n, I can combine them and I say a power m minus n. So for example, x squared over x power 1 should equal x 2 minus 1, which equals x. Last one is just sort of an identification identity, which is a callback to our last lessons in polynomials. Identification. So if we have a to the power x equals a to the power n, then x should equal n, where a is not equal to negative 1, 0, or 1. So what that basically means is, if I have a base, for example, 2 to the power 3 equals 2 to the power x, I can solve for x because I know that 3 must equal x. So simple identification problem. Okay, so let's take a look at a few examples involving exponentials. And when we solve exponential problems like this, quick tip I have for you is to try to get the bases the same. Because if we get the bases the same, meaning the number under the exponent, if we get the bases the same, then it's going to unlock all of those properties like quotient rule or product rule that we can use to help us identify what the variables are. So this first example, we have 4 to the power x equals 1 over 16. Obviously, the bases are not the same right now. What I want to do is this 16 looks a lot like 4 squared, right? So let's change this into 4 to the power x equals 1 over 4 squared, right? 4 squared is 16, so we're allowed to do that. I'm going to continue to change this by saying 1 over 4 squared is the same as 4 to the power negative 2, right? So 4 to the power x equals 4 to the power negative 2. That's our negative exponent rule, right? And finally, now that we have our identification, we have the same base, I can say that x equals negative 2. We're done. All right, same thing for this guy. Well, let's try and get these bases the same. So we have a base of 5 here. Can we get a base of 5 here? Absolutely we can, because we can say that 5 to the power 0 equals 1. Any number to the power 0 equals 1. So I'm going to rewrite this equation as 5x squared minus 1 equals 5 to the power 0. And from here, clearly we see that now the bases are the same, so we can do the identification again. That means x squared minus 1 equals 0. Therefore, completing the square, 0, that means x equals negative 1, and x equals 1. All right, last one. We have 9 to the power 2x plus 1, and we have negative 27 to the power x. This one's a little bit trickier. But again, what we want to focus on is trying to get these bases to the same. So what we're going to look at here is 9 to the power 2x minus 2x plus 1, Well, this looks a lot like 3 to the squared, right? So let's rewrite this as 3 to the power 2, right, to the power 2x plus 1. And this 27 is basically 3 power 3, right? So 3 cubed to the power x, and that's going to be equal to 0. So now we have the same basis. We can start doing some stuff and combine them, right? So in this case, what we could do, let's move this guy over to this side, and let's combine these powers. Remember, this is the exponent rule, so we multiply. This becomes 3 times 4x plus 2. I'm going to move this guy to that side, equals 3 to the power 3x, right? We multiply these guys as well. So again, now we have the same bases. Let's solve. So 4x plus 2 equals 3x. Let's move the 3x over to this side and the 2 over there. We end up with x equals 2. All right. So again, trying to get the bases the same, and then using our exponent rules to help us solve for it. All right, guys, so for this next example, what I'd like to look at is a slightly more complicated problem, which involves a series of simultaneous equations using exponents. Now, what we're going to look at here is, again, the same strategy. We want to try and make the bases the same number. So when I look at a system of simultaneous equations like this, what I see is this 4 can easily be translated into 2 power 2 to the power x, and this, let's keep it as 2y. This 16 also can be translated into 2 power 4, right? 16 is 2 to the power 4. So now that we have everything in the same base, we can start to do some identification. Let's do this power rule. So 2 to the power 2x times 2 to the power y equals 2 to the power 4. And since they're multiplied together, we're allowed to add them, and they have the same base. So 2 to the power 2xy equals 2 to the power 4. Now we have our first simultaneous equation because we have an identity right here. 2x plus y equals 4. Over on this side, again, we're looking to make everything the same base. So what I see is all of these things are sort of factors of 3 in a sense. So, we have 3y up here, we have 27x. Well, 27 is basically the same as 3 to the power 3, right? So let's keep that 3y up top. Let's put that 3 to the power 3 at the bottom, add in the x. And over on this side, we have 1/3, but basically that's the same as 3 to the power negative 1, right? 3 to the power negative 1. Now let's simplify this. We have 3y over 3 to the power 3x equals 3 to the negative 1. And if you remember division, this means 3 to the power y minus 3x equals 3 to the power negative 1. All right, now we can do a quick identification. Y equals, y minus 3x equals negative 1. And now we have our two simultaneous equations. From here, we're just a quick substitution away. Let's say y equals 3x minus 1. Substitute that into this guy. We'll end up with 2x plus 3x minus 1 equals 4. That means 5x equals 5 and x equals 1. If x equals 1, then let's plug that back into here. 2 plus y equals 4. Therefore, y equals 2. And that's how we do it. All right, guys, so for your practice problem for tonight, I'd like you guys to solve these 3 quick equations. for x. Quick hint on number c. The square root of anything, if I say the square root of x, is the same as that thing to the 1/2 power. Okay, so square root of 2 is basically the same as 2 to the power 1/2.